Thank you very much. I would like to thank the organizers for giving this opportunity to learn so much from my peers and to tell them about the works of myself and my colleagues, some of which are listed here. And to thank the previous speaker for the wonderful survey of many of the works in this area. Actually, as I was sitting here, I was in real time adjusting my slides to try to optimize for the minimizing the overlap, and I will cut down on the amount of introduction because of the wonderful work we've just seen, and focus more on the specific things that we'll be doing in one branch of research, in one application, and the research associated with it. So this will be somewhat biased, but more concrete. And for the sake of concreteness, let me unorthodoxically start with the application, the concrete application of SNARKs. I'll describe one of the things that came out chronologically late, but illustrates the situation where SNARKs are useful, illustrates a concrete working system. And along the way, we'll step back, generalize in light of the properties that we've grown to appreciate, and then go back to this example. And this motivating application is Zero Cash, a decentralized anonymous payment system based on Bitcoin. In this joint work with Eli Ben-Sasson, Alessandro Chiesa, Christina Garman, Matt Green, Ian Myers. It all boils down to Bitcoin. We all appreciate Bitcoin, the decentralized digital currency, and digital means that ownership of coins is represented just by knowledge of some numbers. In order to pay someone, you just pass some number to them, and that immediately trivially raises the issue of double spending, because if you pass the number to someone and it convinces them, you can pass the same number to others, and they would be just as convinced, thereby completely ruining the economy. And the way Bitcoin copes with this is using the blockchain, or this distributed ledger that we heard about, which simply posts every transaction. We see who paid whom, how much, and when. And whenever a new transaction is recorded, everybody else knows to avoid respecting the coin that has just been spent. The problem there is privacy, because this blockchain contains all of the information. As consumers, anyone can see our purchases, who we paid whom and how much at what time. The merchants have their cash flow exposed to the competitors. Anyone can see your balance as you go down the street paying merchants and maybe relieve you of some of it. This clearly is a problem. It's been recognized by many. There are some ways maybe to try to dismiss this, like saying that Bitcoin is pseudonymous, you don't really publish your name in transactions. But most users use a very small number of these pseudonyms, of these addresses. And there are many works showing that the transaction graph can be analyzed to de-anonymize people by tracking cash flow and tracking patterns. Another issue is fungibility. Because coins have their history associated with them through the blockchain, different coins may have different value depending on that history, which could ruin the equivalence of different coins. The fungibility are underlying the notion of currency. So we started off creating a decentralized system to avoid trusting a bank. But with respect to privacy, we made just things much worse by having to trust everyone not to look at the ledger and see our private information. Clearly not a reasonable way to build a currency to bind all currencies. So there's been a lot of attention paid to this, many ad hoc solutions. The problem with many of them, with most of them, is that they rely on some activities, some mixing, some mix nets that are required essentially to launder money, to mix your money with that of others. That requires conscious effort, which honest users probably will not bother going through, but criminals will. So we're getting the worst of both worlds. And we took a step back and said, can we build a currency in a way that is inherently private? And that's indeed what we achieved, a new currency where anyone can pay each other in a completely anonymous way. There's still a notion of a blockchain, but instead of recording everything, there are just some pseudo-random values and zero-knowledge proofs recorded that reveal nothing about the source destination amount of payment except to those participating in that particular transaction. Jumping again ahead, because in light of the previous talk, we should be a bit dubious about anything using SNARKs. So here are some numbers. We are going to use some proofs. They'll be less than 300 bytes long. It will take just a few milliseconds to verify them, less than a minute to create a transaction. And there will be some system parameters, that those public parameters or common reference string that require trusted setup. I'll discuss this later. They are less than a gigabyte in size, which is much smaller than the Bitcoin blockchain, so that's well within practical. And there will be some cryptographic assumptions. We'll be using some pairing-based crypto. We'll be using SHA-256 with some standard assumptions about it, and knowledge of exponent assumptions. I'll allude to this as well later. So what is the approach of Zero Cash? Well, the idea is to use SNARKs to rely on proofs. And maybe a good intuitive way to appreciate this is to look at the situation when one party, a sender, would like to send some amount to a recipient, and they have the records that prove that they know who they got the money from and that they haven't spent it. So the sender is convinced that the information is legit. The recipient, of course, is not. The Bitcoin way of doing it is just send it over, and the recipient will verify it. Of course, violates privacy, so we wouldn't do that. Imagine instead if we could somehow have an accountant come in and apply some predicate to this to these financial books. Apply some decision algorithm to check them, and then issue some signature attesting to that fact that the books are good. Well, that would be convincing, but in the real world, we don't have accountants accompanying anyone who's trying to make a payment. But we do have the algorithm that the accountant would have run. And that's something that we can try running virtually in the sender's mind, and then producing a proof that this algorithm accepted these financial records as a witness for this payment. Generalizing this, we have some NP statement, we have some NP witness, there is some NP decision algorithm, and there's a proof. And let's see what properties we need for this to actually work. Well, we need the proof to be convincing, and we will have to relax this notion from proofs, from perfectly sound proofs to computationally sound proofs, or arguments, as we like to call them. This is inevitable due to impossibility results. We would like them to be non-interactive, because not just of this transaction, but also because these proofs will later be posted in a blockchain, so that the recipient of the payment will later convince others that the coin that he received was legit. So it has to be posted publicly, therefore it has to be just a string rather than an interaction. Besides non-interactivity, we need it to be a proof of knowledge. That's a technical condition, but crucial to Zero Coin as well as many other applications. That means that the prover doesn't just, not only do there exist financial records attesting to the statements, but the prover actually knows them, which is crucial because some of the things in these records are signatures by others saying that they actually sent the money to this person. And of course, that signatures exist. The question is, did he ever receive them? And we want these proofs to be succinct. We want these strings to be short so we can put them on the blockchain, transmit them efficiently, and moreover, efficiently verifiable. Yes?
So when you say proof of knowledge, you assume it's zero knowledge proof of knowledge? Or?
Give me 10 seconds. All of this suffice to convince the verifier efficiently, but we still need to protect the privacy of the prover, and that would be the zero knowledge property. Taken together, these things give us a SNARK, succinct non-interactive argument of knowledge, building up on the SNARK terminology of Gentry-Weeks, which omits just the knowledge requirement, and adding the zero knowledge requirement, we get ZK SNARKs. So these are many. We had a list of requirements for ZK SNARKs. Just zero knowledge, well, we know that it exists since GMR, and we know that non-interactive zero knowledge exists for all of NP using a common reference string. You can have some setup procedure, and then to convince that X is in some fixed NP language L, you can set a proof to the verifier with the nice zero knowledge and soundness properties. You can even make non-interactive zero knowledge proofs of knowledge. And they're actually pretty efficient non-interactive zero knowledge protocols for some specific languages with that are essentially simple algebraic statements that play nicely with the crypto. But what about general statements that don't have the right algebraic form? The question is, can we support them in general? Can we have succinct, non-interactive, zero knowledge for all of NP? And by succinctness, just to make things concrete, if we think about the statement that's executed by Turing machine M, running for t steps on some input x that's not too long using a witness W, then succinct means that the proofs are short, constant up to the security parameter, and verification depends just on the input size. If we had this, we could do many wonderful things. We could outsource computation, right? Delegate it, one of those big buzzwords. So we could send information off to the cloud with instructions on what to do. The cloud would come back a year later with a claim that they know the results. And well, if we could create a proof that convinces the verifier that the result is correct, then we wouldn't have to trust the integrity of the cloud. We could just send it to the cheapest bidder and still trust the result, efficiently verify it. So some of you may have seen our demo on stage at Crypto 13, where we had EC2 solve a traveling salesman problem for us, send us a QR code with the result, and we verified it in a few seconds on stage. The proof was a few hundred bytes. The computation was done out there on the cloud. So this is conceptually very appealing. And as you know by now, the general case is not quite economically appealing yet. If you want additional big thinking, cloudy motivations, then the information technology supply chain. If you're applying for grants, this is a good one. So the problem is that everybody's buying hardware from the cheapest bidder, and they're trusting the results of that. And even the U.S. military is finding itself deploying to Iraq and Afghanistan computers that turn out to be counterfeit and could at least potentially contain malicious hardware and malfunction at a critical moment. We actually know that Chinese political scientists say that they shouldn't bother building carrier ships when they could just make sure that the adversaries' carrier ships malfunction at the right time. So as you can see, SNARKs are well justified, and the question is, how do we construct them? Well, we just heard a lot about it, and there's been an amazing progress in a few years. We've actually known for a while that short, non-interactive proofs and zero-knowledge proofs are possible, starting with Kilian, Mikali, and the extension by Valiant. Those were based on full-blown PCPs with Merkle trees on top and random access and the random oracle to navigate the Merkle tree. And that's a very beautiful feasibility result. And we actually have an ongoing project to implement this. We have, not yet published, but working in our lab, full PCPs proving simple statements. The overheads are very large, but it's not galactic. It's something that we can run experiments for. Yes?
What Mike alluded to in his talk, what are the bottlenecks for short PCPs, and why do the linear PCPs currently have smaller coefficients, smaller constants?
So let me answer that in a sec. Still staying with the full-blown PCP track, we even have a good understanding of what exactly is needed here. Random oracles, well, they're not. They clearly say that we don't understand everything, and there is a tighter characterization. We know that SNARKs exist if and only if there exist extractable collision-resistant hashes. There are constructions both ways. Extractable collision-resistant hashes are basically CRHs with the extra property that if you output an element in the range of that function, a digest of something, then you actually know that something. So it's a non-falsifiable knowledge type assumption. And in this paper, we give a bunch of candidates, including knowledge of exponents and also others closer in spirit to LWE. I encourage you to cryptanalyze these assumptions. Little is known about them. The problem is these are still based on PCPs, and the new results, the newer results on the left side of this slide take a different approach based on linear PCPs. And this paper of BCIOP gives a very nice characterization of many of these results in this framework of linear PCPs. They don't originally phrase it this way, but I think it's conceptually the right way. The intuition for why the proofs are more efficient is that we shift some of the weight from the combinatorics to the crypto. If you look at the full PCPs, they spend a lot of resources to make sure that there are certain linear structure in between the elements of the proofs. And using the knowledge of exponent assumption, we kind of get this for free. We know that certain things can only have been constructed by linear manipulations, and therefore many of the checks can be skipped. It's a very high level. So there are many protocols here and many implementations. Many of these are based on the GDPR protocol, preceded by protocols of growth and LIFMA that set up the stage. And we can, there are many ways to slice this progress. Let me just focus on one of them due to time constraints. And this is if we focus on SNARKs for general C programs. So perhaps more theoretically for RAM machines, but to make it concrete for potential users, let's go for the full things. C programs, take a C program and compile it into a version that not only produces the outputs, but also produces a proof that the output was correct. So we know since Kilian and Mikali that this is in principle feasible. You can produce a proof for a single computation. We've also learned that it's possible to do this for ongoing computation using proof-carrying data, where proofs concatenate. It goes back to Valiant and extended by Chiesa and myself. We have, using the GDPR and the PGHR protocol, and improvements thereon, we've greatly improved feasibility and the efficiency of verification, leading up to actually working prototypes for small C programs running for a short amount of time. Then this can be extended by allowing any C programs using universality, basically having a universal processor that is a von Neumann architecture. It gets its input, it gets its program as an input and runs it, and that means you can you can construct that setup parameter once and then support any program, and also you can using these tricks of proof composition, extend the proof step by step, thereby making things scalable and supporting programs running arbitrarily long with just a essentially multiplicative constant overhead in both time and memory. So you can think about it as a processor that just runs a program in a secure way by issuing proofs, and it has constant resources as a function of the security parameter and the original program size. It does not grow with the length of the computation. And of course, the consumption of the memory consumption of the original program, not just the size. This processor has a well-defined Hertz rating. Right now, it's measured in decihertz, which is kind of too slow for practice, but at least it's well defined, unlike previous constructions where the size of the processor would blow up as it computes. The big issue here is still the proving overhead. That's the main challenge for practicality, and that's what currently limits applications like outsourcing to the cloud. Whole new branch is doing things in a tighter way by program analysis and non-generic reductions. We've just heard about it in the previous talks. This is one of the things that I cut out, things like Geppetto, Buffet. They have much tighter reductions quantitatively, but at a cost in universality, in supporting random accesses and the general control flow, except for Buffet, where it does support it, but with a fallback to a performance that's comparable to these systems. And one of these is the one that we actually use in Zero Cache, which we'll get back to in a sec, yes.
What do you mean by network hosts?
That refers to continuing the computation. Imagine that you have a data center full of machines, none of which are trusted. You would like the first machine to produce an output and along with the proof of it, and the next machine would consume that, work on it, and produce a new output with a new proof, and you maintain the invariant that every value flowing in your data center has the proof associated with it. All of these are publicly verifiable.
So then why don't you get any hopes in all of them then?
You can if you just concatenate the proofs and all of the values needed to check the proofs, the instances. But if you want succinctness, if you want to check only the last value, then you need something more. Yes?
Can you elaborate on what do you mean by at the cost of the universality? I thought Michael Walfish, when just gave a talk, and he said Buffet supports any C program, so it is universal.
Right, so that's a qualification I gave. In order to support universality, you need to
Buffet is not universal. I mean, I'd love it if it were, but it's not. What he means by universality is the same circuit can actually verify multiple different programs. That's not what's going on in Buffet.
You're talking about the recursive composition.
No.
No?
He's talking about representing a processor as a circuit. And then once he's representing a processor as a circuit, he can, for any computation of that length.
Yeah, but that's not an efficient approach.
Well,
You just want to be able to support
That's
it.
exactly the claim, yes. The tightest approach are not universal, and in order to exploit the tightness, you give up on the general random accesses and the general control flow.
So universality just means you want to be able to do any program. But it doesn't mean that you actually have to go through a universal circuit. There are ways that you can optimize that, and not everything has to go through the universal circuit.
Right.
Maybe for some parts you don't have to go through
Right.
that.
Yes. Okay, so to build such a system for general C programs, you have to go through quite a stack of reductions. We have the underlying SNARK prover and verifier. They get some input and weakness or auxiliary input to produce. The prover produces an output and a proof. But these are for some algebraic construct, and if you start with a C program, then you need to go through a series of reductions. We have a couple of papers explaining and proving the soundness of these reductions, going from C programs, in our case, to support universality through some specialized CPU architecture, a RISC machine we call TinyRAM. Then we lay that out as a constraint satisfaction problem that fixes the topology and assign that to algebraic variables. And all of this is fairly expensive, and it does contribute about 2 orders of magnitude overhead as a rule of thumb compared to tighter approaches. For Zero Cache, to avoid these, we actually tailor things in a much, much tighter way. Let me tell you about this. How are we doing on time? Okay.
Are you going to give some concrete performance numbers? Do you have concrete performance numbers for the recursive composition, recursively composed SNARKs?
I can give this now. If you do the fully universal version with scalability, with the recursive composition, that gives you that CPU on the order of a decihertz. That is about a cycle of the CPU, advancing it and producing a proof takes about 10 seconds. And that's that's without multi-threading or GPU acceleration or anything of the sorts that would be naturally applied if you really put your mind to it. So it shows that it's doable, but not yet appealing.
Use that takes 10 seconds.
Yes. Let's take this offline. I have some additional numbers for trade-offs. Okay, so for Zero Cache, let's see how things are instantiated to get a feel for what you do if you actually wanted to get a practical application nowadays without going through all the extra levels of abstraction and reduction. Let me go take you through a series of toy examples leading up to the full scheme. The most basic way to build anonymous cash, not very well, is just to have a bunch of serial numbers out there, and in order to create a new coin, you prove that you're eligible to it. For example, that you've just burned a Bitcoin, and that makes you eligible to a serial number. All the serial numbers are posted, and in order to spend the coin, you just say, okay, I'm using a coin with a given serial number. Makes sense, except no privacy whatsoever. Anyone can link the spending event to the minting event. To solve this, there's a very elegant approach of Sander and Tashma, preceding decentralized currencies. And the idea is to use a commitment scheme where every coin has several values associated with it, a serial number, a commitment to the serial number using some randomness, using a hiding and binding commitment function. And to mint, you say that you spend a Bitcoin to create a coin whose commitment is CM. Only you know the serial number. So brown is private, blue is public in the ledger. And all these commitments are public. And now, well, to spend the coin, you can just open a commitment, right? You say, okay, I spent the coin with the serial number, and here is the corresponding commitment and the randomness to link the two, and anyone can verify that the serial number is unique and matches the commitment. That's not private either, because again, you expose the commitment that you posted earlier, so minting and spending can be linked. So the idea of Sander and Tashma is to use zero knowledge proofs as follows. We build a nice big Merkle tree using a CRH on top of all the commitments, and then we prove that, when we spend a coin with a given serial number, we prove that we know the coin randomness and the commitment that's in the tree, such that these two match the CM, but we don't tell which one. So all of this is done using a zero knowledge proof, and it requires, to be convincing, a proof or an argument. It needs to be non-interactive, so people can broadcast that. It needs to be zero knowledge, so nothing is leaked about the CM that could allow linkability to the minting. It should be a proof of knowledge, and it should be succinct, so ZK SNARKs. Okay? So we can already do a very basic scheme using ZK SNARKs to instantiate Tashma standards. But once we do that, well, we can use the NP power of ZK SNARKs to get additional functionality that was not achieved by any of the prior attempts at anonymity for Bitcoin. For example, you can add variable denominations, coin with different values, by adding an extra commitment. And go over this very quickly just to give a feel. I know we won't have time to verify the details, but to mint, you say that you spend V Bitcoins to create a commitment, and you actually reveal the value, it's public, and you also reveal the randomness for an outer commit, but there's another extra commit down there that you do not reveal, and to spend, you actually reveal everything and show that it's consistent, protected under zero knowledge. We can add direct anonymous payments, supporting payments addressed to people with some permanent addresses without revealing where the payment's going. So that requires some algorithm to create an address pair, and then the coin structure becomes much more complicated. Now there's a couple of commitments, some PRF, to derive the serial number from the secret key, and the public key is involved in creating the commitment. It's pretty tricky, and well, you can set things up so that minting and spending are analogous to above. Basically, to use up a coin, you create a zero-knowledge proof that the values you have are consistent with the commitment, with some commitment in the past, and you reveal the serial number so everybody makes sure you're not double spending. And the sender can decrypt using his secret key, and thereby get all of the values needed for them to use up that coin. Now, all of these and many more details are elegantly summarized in what we call a poor transaction. And you can think about the poor transaction as a primitive for direct anonymous payments that generalizes sending payments, merging coins, making change by splitting coins, providing transaction fees, and many other things. It consumes old coins, it creates new coins, it gets instructions on what is the value and destination of the new coins, and it outputs things that will be put in the ledger that consume the old coins, create the new coins, and include the proof that the old coins were indeed valid, and that, crucially, the monetary invariant was preserved. The total value of the new coins equals that of the old coins. All of this is the NP statement, what's verified by that virtual accountant, and that's what you find in the ledger. So this NP statement is tailored to Zerocoin, and we implemented it in the underlying language of QAPs, following GDPR, PGHR, and our improvements on them. And you can actually see what a transaction looks like. You can see the current Merkle-free root, serial numbers of the consumed coin, commitments, ciphertext addressed to the recipient, so you can get the ownership on the coins. A bunch of other things dealing with non-malleability, I won't get into that. And the zero knowledge proof, which is, small enough to fit on a slide. Now, this is properly formalized in a primitive, decentralized anonymous payment system using algorithms to set up the parameters, create addresses, and so on. And there are security notions, distinguishability based. I'm very optimistic about the new simulation-based alternatives that Elaine presented. These are the ones we used. You can see the details in the paper. There's a full working prototype. I mentioned the numbers earlier, and we actually simulated all of this on the Bitcoin scale economy. We replayed Bitcoin transactions on EC2, and it could keep up with the rate of transactions on Bitcoin, which is non-trivial and could not be said for some previous constructions that had even less functionality. Trusted setup is a big issue here. The trusted setup essentially creates a template for what a correct construction looks like, and that template is about 1 gigabyte in size. If that setup is corrupted, then the soundness fails. Fortunately, privacy still holds, and we have an MPC protocol to address that. We can set up a ceremony with n players, suffices that just one of them is honest for the currency to be sound. It's not as good as eliminating it, but I think in practice it's close to satisfying. So taking a step back, let me mention some open problems for SNARKs in general and for Zerocash in particular. One is reducing the proving time. Right now, it takes less than a minute, say 47 seconds on my desktop, to create a transaction. It's okay, comparable to the 10-minute blockchain update rate, but we could hope for better, and certainly for other applications we need much better. Pre-processing is a big issue. It could be achieved either by better PCPs that take us back to those constructions that do not have trusted setup, or maybe some completely other approaches. I think it's a fascinating problem. We don't know much in the way of impossibility, and so far, I think we've only started to explore the landscape. More applications are.
Don't you need trusted setup for zero knowledge? Don't you need like a common reference string for zero knowledge?
That's a good question. I'm not sure. But it's interesting even without zero knowledge. We're looking for more applications, in particular ones where we have very tight reductions, creating small NP statements that can be nicely expressed in the underlying language of the SNARK. And the fascinating PL work that's begun doing this in an automated way. Many interesting challenges there on the PL and optimization perspectives. And on the theory side, can we base things on more assumptions? We know that the general PCP-based SNARKs can be done on general ECRHs, and knowledge of exponent gives us just one family. What about the others? Can we build SNARKs on the LWE style assumptions? Can we build SNARKs that are sound in the presence of quantum computers? Since time is out, let me just give 3 URLs for our work on SNARKs in general, for our works on Zerocash in particular, and our source code for LibSNARK that includes implementations of most of what you've seen. Thank you.